So first of all, I'd like to welcome you all to this webinar, which, as you can see, concerns ProCalc. And what we're going to do today is to create some biomechanical calculations in ProCalc. So my first job is to switch to the next slide. So this is essentially what we're planning to do. A short ProCalc introduction, just telling you a little bit about what it is. I hope and think that most of you have come across it or heard about it at least before. Then we're going to add some calculations to the variable scheme. We're also going to add some events and some variables and events. We're going to use the variables and the events to calculate some cool parameters, which we will then process in Nexus and have a look at, and maybe even Excel if we're lucky. So hopefully that sounds good to everybody. Just to summarize, what is ProCalc? It appeared a few years ago, maybe 5-6 years ago by now. The latest version is actually up to ProCalc 1.5, which has added some interesting features for Theia or markerless calculations. Actually, ProCalc is very much a companion app to Nexus. So in case you have a Nexus license, you also have automatically a ProCalc license. But the distinguishing thing about ProCalc is that it does have its own graphical user interface for creating models and calculations. But very importantly, Nexus also has a ProCalc pipeline operation, which enables you to take any of those calculations that you have created using the ProCalc app itself and just process in routine processing. So perhaps the most important thing to note about ProCalc is that unlike quite a lot of other solutions for biomechanical modeling, you do not have to know any programming or script language in order to use ProCalc. You can simply use it as a graphical user interface-based application. So what are we going to do today? Well, we're going to look at data from a reaching study, which I was very kindly given by the Sunnaas lab in Norway. So it's a simple upper body marker set along with a marked up cup, and it's essentially a reaching type study. And the task for the user, sorry, not the user, the participant in the study is to drink from this cup. So it's a simple experiment, but it opens up some interesting possibilities for calculations. This is what the marker set looks like. It's very basic. It's got 2 shoulder markers, 1 clavicle, 1 on the forehead to just pretty much show you where the position of the head is, a single elbow, a single wrist, and a single hand marker. And then you have 3 markers placed on the cup itself, as we can see. So that's the marker set. The question then, what are we interested in? Well, this could be a lot of things. So for the purpose of this particular webinar, I have only picked out a few things. So we could, for example, look at the variables such as the shoulder angle or the forward trunk lean. We could look at the events such as the instant in time when you pick up the cup, when you're starting to drink, and when you put the cup back on the table, for example. And the parameters that you can then derive from this would be things like the time it takes you from the pickup until you actually drink. So from here to here, and the maximum forward lean that the participant uses in order to reach the cup, whether the participant sits steady and brings the cup forward to the mouth, or whether the participant chooses to lean forward in order to get the mouth closer to the cup, that kind of thing. So that pretty much sets the stage for what we're going to do. So then I'm going to waste no further time and get going in ProCalc. We have a static and we have two trials in this case. They are actually from two different subjects. The static we're going to ignore, that was used to set up the marker set, and the marker set has been covered in the previous webinar. This is the first trial. So as you can see, the subject grabs the cup, drinks, puts it back. Very, very simple. The second one is interesting because of two reasons. One is that it's a left-handed subject instead of a right-handed one. And the second one is that this person leans a lot further forward in order to get close to the cup. So it's two interesting trials that enable us to maybe have a look at some different variations. So let me just quickly get my little cheat sheet that I use to keep track of where I am in this process. Okay, so the first thing we do in ProCalc is to start creating calculations schemes. So after we load up a trial like this, so we load up this one and maybe have a look at it, we can start generating variables. Typically, we would use, we'd start with the variables. Input parameters would be things like subject parameters or constants that you may or may not want to use. So if you, for example, want to use a knee width or an ankle width, as in typical gate models, you might specify those in the input parameters. We shall skip that for now. It's also covered in some tutorials online if you're interested. What I shall do today is start a brand new calculation scheme, and I'm going to call it webinar. And I'm going to start adding variables. So it's very important, obviously, to plan what you're aiming to calculate. So needless to say, I've done this already, and I've even practiced a bit. But so I'm going to start just diving into these calculations. The idea here is that I'm going to show you what's possible, and I'm not going to explain in great detail why exactly I've done it in this particular way. I get a message here that the sound is a bit unsteady. Maybe I'll try and move the microphone a bit closer to where I'm sitting. Hopefully that might help. So the first thing I'm going to do is actually to create an up vector. Just a second. The up vector I'm going to use in order to create a body segment. So what I'm aiming to do here is to create a segment that represents the orientation of the thorax or the torso. So the first thing I'm going to do is create a body up vector. So I'm pressing the add button here first. I'm typing in body up vector. I'm selecting from the menu here that I want to create a vector. And I'm selecting, I want to create this vector from point A to point B. Then I click here, and then I click here, and that's it. I've got my up vector. So of course you could do this much more advanced, but in this case, this is going to be my reference up vector. Okay. Now, following on in the same spirit, I shall try and create a body forward vector, which I'm going to use another variable for, namely I'm going to calculate a halfway point, halfway between shoulders point, which is a point which is halfway between A and B. I click on the shoulder markers, and here I have it already. And this enables me to create another vector, which I can use actually the copy function from the first one. Instead of body up vector, I call it body forward vector. And I select the halfway between shoulder and the clavicle. Okay. So now we have a vector that points forward in the body, one that points upwards in the body. Now we want to create one that points leftwards in the body in order to generate all the relevant body axes. Now the first challenge actually appears already, because we're using the same marker set for both left and right-handed people. And in this case, we have a right-handed person, and the shoulder marker is on the right-hand side, and the opposite shoulder is on the left-hand side. Now, this would be the exact opposite case if we had a left-handed person. So how do we solve this problem? And this is when we start with some mathematical concepts, which I hope you are familiar with, because we are able to actually use what we call a vector dot product in order to ascertain this variable. So what I'm going to do now is to create a what I call left-right dot product. And this is also a vector function. And here we have the dot product of A and B. Now, what I can do here is take a body vector and dot product it with a lab vector. And in order to get the correct body vector, I need to add a vector from the shoulder to the opposite shoulder. So body, shoulder vector, I shall call it. There we go. From A to B again. That's usually how we create vectors. So now I have the shoulder, shoulder to opposite shoulder vector, and this is actually the one I want to use as input for my dot product. And the cool thing if the shoulder to opposite shoulder vector is aligned in the same direction, I get a positive value here. Whereas, and I'll prove this to you, if I go and open the other trial, which is the opposite way around, and I look at the left-right dot product, I get a negative value. It's one of the features of the dot product calculation. I encourage you, in case you're not familiar with dot products, to read up on it. I can't explain this in more detail now, unfortunately. So here comes a pretty cool function in ProCalc, which is that ProCalc can also evaluate if statements, as it were, or conditional statements. So what I can do now is actually to generate a body left vector. as a comparison. And if you look at the comparison group, you see a few different options. And what I want to do use here is if A is bigger than B, then C else D. So essentially, this enables me to fill out these drop-down boxes here. And I've just calculated my left-right dot product. I need to compare this to another number, and I'll compare it to itself multiplied by 0. So this factor here I can use to actually cheat a little bit and compare my left-right dot product with 0. And if this is bigger than 0, I'll return the body, the shoulder vector times 1. Whereas if it's smaller than 0, I shall return the vector shoulder vector, but with a factor -1, so flip it essentially. So as you can see, body left vector is now pointing leftwards for this trial. I'll save it, check that this is also working on the other side, variables, body left vector, and here we have it, also pointing leftwards in this case. So that's one solution to the problem of not knowing in advance, or then I don't have to have two separate models, one for left-handed people and one for right-handed people. I'll pop back to my original trial again. Okay. Another little trick in ProCalc is that you can group things by either alphabetically or, for example, by type. And I find it easier sometimes to group them by type, because then I have all the vectors in one group and all the numbers and points and stuff in a different group. Good. So now we can go ahead and create a body segment. And select creating segments is always easiest when you have two vectors and an origin point. So I'll go and create the trunk segment, I'll call it. And the segment is what I want to create. And when I want to create a segment, I need to either base that on 3 points, or on 1 point, which is the origin, and 2 vectors, which are these. There are also some more advanced options, which I will not cover in this particular tutorial. So what we want here is for the x-axis to point forwards, we want the y-axis to point to the left, and we want the z-axis to point upwards. So we can use origin A, z-axis B, and use the up vector. And then we have the y-axis. The x-axis could be the cross product of B and C. How does this work? Well, first of all, I click my origin, could be the clavicle. The up vector we already defined, and the cross product of the up vector and the left vector should be the forward vector. And in this case, very illustratively, it's now pointing backwards, which we can easily fix by flipping the vector with a factor of -1. Okay. So here we go. Here we have our body vector. Very straightforward. Like that. So now we can go on and create some more vectors to create a different body segments. So for example, we can create a upper arm vector. Again, we go ahead, select vector, and when you're selecting points, you can either do the drop down, or you can actually click directly in the workspace like this. So now I get the shoulder vector, and then I create a copy of this, call it the lower arm vector, and create this vector. And these two vectors I could now use to define my shoulder segment. It's similar to the way it's done in plugin gate, except that I ignore the fact that the shoulder vector isn't, the shoulder marker isn't exactly at the joint center, but it's these markers will move well enough with the anatomy to be reasonably accurate. So what I'll do is take my trunk segment, make a copy, call it the shoulder segment, select a different origin, the shoulder in this case, and I'll take the upper arm vector and the lower arm vector as my defining vectors. And in this case, we have, as you can see, we need to choose a different axis orientation. So we take the z-axis as the basic, and the y-axis is now the cross product of the two, in order to get our x-axis pointing forwards in the anterior-posterior direction, and the y-axis in the medial-lateral direction. Okay, fantastic. We have two segments. Now, what's also useful is to have a subject reference frame in case the subject is facing not in the same direction as the lab, for example. So you could, in order to get progress angles, for example, it's useful to have a reference frame which isn't necessarily the lab reference, in case the subject, or it's a bit like in a gate lab. If you walk in one direction and in the other direction, you need to know the reference frame of the person in question in order to calculate the progress angles correctly. So there is a nice function in ProCalc for this particular purpose, which is, which I'll show you in this now, we'll call it the subject reference. And in this case, what we want to do is create a segment with an origin and an x-axis that is closest to a certain axis that we have already defined for our subject. And z-axis is the lab up direction. So if I select my clavicle as the origin, it doesn't really matter exactly which one it is, and I select the body left vector as, the body forward vector, of course, as my x-axis, then what we see here is that ProCalc has aligned the forward axis with the lab axis that is closest to the forward axis. So this just enables the subject to sit in different directions. You don't have to align the subject with the lab axis. Right. So this again allows us then to go ahead and calculate some angles. For example, here's the shoulder segment, here's my trunk segment. It's kind of interesting to know what is the angle between these, which would obviously be the shoulder angle. So I'm going to go ahead and calculate the shoulder angle. And this, in case you hadn't guessed, is the function type is an angle. And here you get the Euler angles, as well as other types of angles that you can calculate between individual vectors. The continuous Euler angle options are actually in case the angle goes through a 360-degree rotation in order to maintain the increasing angle so that you get to 360 or 400 degrees. If you calculate in a pirouette or something like that, you might not want it to return to minus 180 once it hits 180 or something like that. In our case, in this case, it's not actually that important because the shoulder doesn't go through those kind of range of motion in this case, at least. So I'm going to choose the YXZ Euler angle decomposition, which means that we take the flexion extension first, the abduction second, and then the rotation, of course, third. My parent segment is the trunk segment, and my child segment is the shoulder segment. And here you see the angles that we get. Looks roughly correct. We get a bit of the red curve. I'll make this a little bit bigger. The red curve is the flexion extension. The green curve would be the abduction, and the blue curve would be the rotation in this case. We could also calculate the thorax angle. Thorax relative to our I'll take this a YXZ, and in this case we want to use our trunk reference, sorry, subject reference as our basis. So here's the thorax angle relative to our subject reference frame, and we see that the subject is leaning forwards. If we want the subject leaning forward to have a positive rather than a negative value, we can also negate individual components here, like so. So if this corresponds to our biomechanical / anatomical expectations better than the other one, then we can simply negate any of the individual components. So there we go. That's our thorax angle for this particular subject. Doesn't change very much, but on the other hand, we might see different results if we go and look at our second subject. Here we have the flip I was talking about, in which case we could potentially use the continuous Euler angle YXZ. That didn't help very much, so I shall leave that for now. And I think I may have made a mistake somewhere. Trunk segments, shoulder segments. I guess okay. Well, this is a demo effect, so I shall look at that later and continue with the webinar instead. Back to here, variables, thorax angle. Okay, so the next step in this particular experiment might be to calculate some distances. Now we've been concentrating on calculating angles between segments, for example. But we also might want to know, in order to be able to identify events later on, distances between different markers or different calculations in this experiment. So the first thing I'm going to do in order to establish the position of the cup is actually to create a new variable called average cup, which is nothing other than the average of A, B, and C, i.e. the 3 markers on the cup. And of course, if you take the average, then you get like a decent estimate of the actual position of the cup. I'm not 100% sure exactly how these were placed on the cup, but that's yeah. So this is just to illustrate this particular calculation, and then we can go ahead and add hand to cup distance, for example. So here we have another calculation called distance to A, from A to B. So we can then choose as our A hand, and as our B we have the average cup here. So here we can see the distance being calculated. Starts off at 350 millimeters, and then obviously gets a lot smaller as the person reaches out for the cup, like that. Okay. Another interesting and similar calculation might be the distance between the face and the cup. That might help us when we try and determine when the person is time to drink. So we'll make a copy of that and call it face to cup distance. And instead of the hand, we'll choose the, let me see, head marker. Exactly. So this distance will obviously be quite small when the person is actually drinking, and much bigger when the person is putting the cup on the table. And another type of calculation you can do, which is also very, very handy in ProCalc, is to calculate the distance between something's initial position and its current position. How do I do this? Well, in this case, I'm going to calculate the cup vertical displacement. And this is also a distance, and it's also a distance between 2 points. Interestingly, it's a distance between the average cup and the average cup, which obviously is 0 unless I change my timing of when I evaluate the first one to be only at the first valid frame. So this effectively creates a distance between the average cup at the first valid frame in the trial and the current frame. And I can even go ahead and only do this in the Z direction. Okay. So what we see here is a calculation of the distance of the cup, or how far the cup has been raised dynamically. And this can also be useful when we try and determine whether the cup has been lifted or not. It's obviously, if this distance is 0, it's pretty much guaranteed to be on the table. Another variable that we might find useful when determining whether or not the cup has been lifted is its velocity. That's another thing we can easily calculate in ProCalc. So we go ahead and add another variable, cup velocity. And in this case, we have the velocity function, of which there are two velocities and two angular velocities in case you are calculating an angular velocity. The 5-point function uses a 5-point numerical function, and the other one uses a 3-point. That's kind of not really important. I always use the 5-point. And this is what you get. So you get a vector that has 3 components, which is the velocity in x, y, and z directions, like this. Now, perhaps what we are even more interested in is the cup's absolute velocity. How do we do this? Well, it's also easy to calculate. Cup velocity magnitude. In this case, we have under distance, there is magnitude of something, and then we simply select the cup velocity here. So as you can see, in this case, the cup goes from 0, or pretty much the only thing is numerical instabilities at this point, and then the speed goes up to almost a meter per second before being quite low as the person is drinking, and then back again. Not very surprising, but still a very useful thing to be able to do calculations with. Okay. Next step. The final thing that, or the final couple of things I want to calculate in my variable scheme, which is already starting to grow a little bit in size, but we've also calculated a fair number of different cool things here. The next thing I'd like to calculate is actually the cup's angle. So I want to use the cup's angle as a variable when I determine whether or not the person is drinking, because clearly in order to drink from a cup, you need to tilt it. So the first thing I'm going to do for this is to create a vector, and I'm going to call it the cup up vector, like this. And of course, this is a vector again from A to B, as we've done now multiple times. And I'm going to use these two markers, assume that they're relatively vertically placed. Looks a bit like it. So that's the cup up vector. And the final thing I'm going to do in this for this one is to calculate the cup tilt angle. Cup tilt angle. This is an angle, obviously, and in this case, all I want to do is to calculate the angle between two vectors, namely the cup up vector and the lab z-axis. So here we get that. And we can see that the subject is indeed tilting the cup as and when the subject is drinking, and placing it back flat again, flat-ish. The markers are probably not entirely vertical, but that's okay. So this is something that I can use as a criteria for determining whether or not the cup has been lifted, or whether or not the person is drinking. The final thing I want to have a look at later is actually the trunks, or how far forward the subject is leaning as the subject then grabs the cup and drinks. Now I could calculate the distance of the clavicle marker from its initial position to its current position, just like we did for the cup's vertical. However, the problem with that is then I would get a positive value if the subject is leaning forwards, but also a positive value if the subject is leaning backwards. So that's kind of not that desirable. I would like a negative value when the subject is leaning backwards. Now this is where another cool calculation can be used in ProCalc, which is the following. I calculate the clavicle in the subject reference frame. And there is a function here to calculate a point where I can transform a point into another coordinate system. So I'm transforming, in this case, the clavicle point into the subject reference coordinate system. Now this is not that interesting in the first instance, the reason being that I've also used the clavicle as the origin of my subject reference frame. So I need to evaluate this only at the first valid frame to start with. And the second thing I might want to do is to just, in this case, skip the y and the z and just evaluate the x. Or was it the y? Okay. Forget that. I'll stick to this version. So this basically allows me to evaluate the XYZ position of the clavicle marker in the subject reference frame, which will be negative if the subject is leaning backwards. Okay. Right, so this essentially are all the variables that I need in order to start generating events. Events are going to be very crucial here because I don't want to sit in Nexus, unless you could, of course, sit in Nexus and manually identify this is when the subject grabs the cup, this is when the subject starts to drink, etc. But this this can be automated in ProCalc, and that's the next step that we're trying to do here. So I'm going to save this scheme. This is now finished. I'm going to hop over to the events, create a new scheme called webinar. And I'm going to use this interface. The first thing I'm going to add is a general custom event. So both Nexus and ProCalc have this this function that allows you to generate custom events. So they don't have to be left foot strike or right foot strike or whatever. You can call them whatever you like. And in this case, I'm going to call it cup lifted. So what do I want to trigger this by? Well, in this case, I'll actually trigger it by the cup velocity magnitude. And I'm going to trigger it when the magnitude of the cup's velocity exceeds 30 millimeters per second in the direction up. So the curve is going up as we evaluate it. In order to avoid possible small fluctuations around the threshold, I'm also going to say that this has to last for at least 500 milliseconds. Now, what you can also see here is that, well, ProCalc immediately then calculates these events. One here, and one here. So these two events are the velocity crossing the same threshold due to the subject accelerating or decelerating the cup as he or she is drinking. And I don't really want those events because this is a cup lifted event. So I want to find a second criteria to avoid these two events being determined. And this is where the extra conditions comes into play, because I can say only when variable, and I've already calculated this because I planned it, the length, namely the cup vertical displacement, is lower than, for example, 10 is lower than 10 millimeters, yes. So in this case, I'm only accepting this event if the velocity crosses this 30 millimeters per second threshold, but only when the variable cup vertical displacement is smaller than 10 millimeters. And as you can see, all the other ones are now no longer being calculated. The second event I want to calculate is, I can just create a copy of this. The second one is start drink. And I'm going to go for an angle in this case, namely the cup tilt angle. And I'm going to determine that the person starts drinking when the angle exceeds 25 degrees, or maybe 30 degrees. Let's go 30 degrees. In this case, the minimum should be a bit higher than lower than 500 milliseconds, because the entire drink might last not that long. And I'm going to remove this extra cup displacement condition. So as you can see, this has determined that the start drink happens here. Seems about right. So that's cool. And I'm also going to then create a end drink, which is exactly the opposite. Which is then when the cup tilt angle crosses the same threshold in the direction down. Okay, so that's happened roughly there. We can have a look at the start drink is here, and the end drink happens a bit later there. And then finally, we could add a an event which is cup back on table, which is then we could simply say that this is when the distance, the length of the cup's vertical displacement is crossing to be below 10 millimeters at the end of this movement. So basically when the person is putting it back on the table like that. Okay, so that's the 4 events that I'm interested in this case. Grabbing the cup, starting the drink, ending the drink, and putting it back on the table, basically. All right, so I now have a whole bunch of variables here. I have a bunch of events here, Now I can go ahead and calculate some parameters. And that's when I switch to the last tab here, add a new one. I'll call this webinar as well, so they're all grouped together. And I can calculate the stuff I'm actually interested in. For example, time to drink. Time from lift to start drink, for example. So this is essentially just a measure of how long it took. So it's a time function, and it's from event A to event B. And here we have the events that we're talking about. So it's from event general cup lifted to start drink, which in this case has been evaluated to 1.35 seconds. We could very similarly copy this and calculate drinking time, in which case we'd start at the start drink and finish at the end drink, which was 0.82 seconds in this case. And then finally, cup back to table, from general end drink to cup back on table. So that's essentially the timing of the three phases that we've been talking about. We could also calculate a whole bunch of other interesting variables. We talked about the forward lean already. So I'm going to add a variable called maximum forward lean. In this case, we want to evaluate a value of some sort. And under value, we have the variable maximum between two events. The variable we're interested in is a point in this case, because we calculated this clavicle in subject reference frame already. And we want to evaluate the x, and we want to evaluate this between our cup lifted and cup back on the table. So this person does not lean forward very much at all. 23.8 millimeters, it seems. So that's interesting, maybe. We can also calculate maybe an angle, such as the forward lean at drink, which is another value, but in this case we evaluate it at a specific event. So we take an angle, an Euler angle in this case actually. We take the thorax angle, and our x is the tilt, and we evaluate this at start of drink. So the forward tilt of the thorax is 25 degrees as the subject starts to drink. The final parameter I wanted to quickly calculate is actually a 3D measure, just to show that this is possible. I'm going to calculate the complete excursion of the clavicle marker. So clavicle distance traveled. And for that, we have actually a group called 3D here. So you can evaluate the distance traveled by a variable between two events. And in this case, we want to evaluate the points, namely the clavicle. And we want to do this from the first valid frame to the last valid frame. So for the entire trial in this case. So for the entire trial, we see that the clavicle marker has traveled a total of 128 millimeters. Okay. This is essentially all I want to calculate for this research project. So I've now completed my work in ProCalc, really. The final thing I could do is actually which I often forget, so I shall remind me and everyone else to do this if it's necessary. If you wanted to calculate and write the thorax and the shoulder angles back to the C3D file, and thus made them available, for example, in Polygon, you need to save to C3D. There is a small little tick box that you have to tick down in the left hand corner here. If you tick those, then the C3D or this variable will be written back to Nexus. So now comes the exciting bit, because now I have my trials from my 100 different subjects, for example, and I have my schemes: variable scheme, event scheme, and parameter scheme. I could go ahead and calculate all these inside ProCalc here by marking the trials in like so, and just hitting process mark trials. I will not do that for just now, because I'd rather do this inside Nexus. So I'm gonna just go into Nexus, and first of all, I'm just gonna open the first trial, and I'm gonna create a new pipeline. In Nexus, under data processing, you'll see there is a run ProCalc operation. Run ProCalc like this, and then you can simply select the exact same, that's the one I played with earlier. Now we have the webinar schemes. So the exact same schemes that we just created in ProCalc, and we can just run these like so. So first of all, you'll see that the events popped up on the time bar in Nexus. So I can go, this is the time of grab, this is time of start drink, end drink, back on table. So that's the first thing you can see. In analysis output, you'll see the different parameters that were calculated. And finally, we have the two angles that we can also look at, like so. Now, of course, we can do the exact same thing for the second trial, where the subject behaves quite differently. Run the same operation. We see that it's had one extra event, so we need actually one more condition to avoid these false identifications. This is obviously one of the things, one of the reasons you would do a pilot study for this kind of thing, to perfect the schemes. But anyway, we still get the different variables, the different parameters that we've calculated. So for example, clavicle distance traveled is 1131 millimeters instead of like a tenth of that for the first subject. I could also now finally go back into ProCalc and process from here in order to output everything to an Excel spreadsheet. This can also be done from inside Polygon here. Polygon, I mean Nexus, of course. But in this case, I've already set it up from within ProCalc. So as you can see, I've got a reaching study XLS spreadsheet already prepared, not prepared, but I I've set it up so I know where it's going to end up. So if I go and open up this document, this is it. What we see here are all the parameters that we calculated, and we can now go and compare the outputs from these two different subjects. For example, the clavicle distance traveled in subject 1 was 128 millimeters, 1131 in the other. Forward lean was 17 and 25. So there's a whole bunch of things that you can then calculate, and of course the idea is to do this on your research subjects so that you can easily get these values out in for whatever purpose, like writing a paper or something. And this is almost exactly 1 hour, which is good planning on my part. And when I say good planning, I mean pure luck. So I think at this point I am very happy to take questions. So if you fancy asking a question, feel free to type in. I apologize for the size of the fonts if they were too small to read. Can we also export the other output parameters to C3D files like temporal spatial parameters for displaying Polygon? Yes, so what happens here is actually that these parameters that end up under analysis outputs. So if you have clearly time from lift to start drink is a temporal parameter. If I save this trial like so, and this was drinking 02, if I go ahead and open Polygon, come on. Well, it's kind of there we go, Polygon 446. They all these parameters, once I'm in Polygon and create a report, I have an empty one for the time being, I import the trial, you'll see that the different parameters are indeed available in Polygon, and you can do exactly the same as you would with the plug-in gate, for example, parameters. The parameters are calculated based on events. What happened in the drinking 02 where it detected the same event twice? Yeah, that's an excellent. I was hoping that somebody might ask that question. And of course, what you can do is just have a look. Was it 02 or 01? Okay. Now I've opened 02, but since I saved out the, oh yeah, sorry, so you see all the 5 events here. One appeared almost behind the 400 number here, so I didn't see it at once. But what I could do is clear these events from Polygon, from Nexus, resave it, and have another look in ProCalc. So basically here in events, I go to the one event that was identified twice, which was, which one was it? not this one, not this one, but this one, general end drink. Yes, in fact, I forgot a step in my, yeah. So what happens here is that it crosses the threshold twice. And if we go back to the variables, we can probably see this straight away if we look at the cup tilt angle. You see this extra little tilt here means that this is being identified twice. Now, in order to avoid this, we could add another condition to the general end drink, such as it has to last for a minimum of maybe 1,000 milliseconds. It is, after all, the only time we want to identify. Oh, well, skip that. That didn't work. That actually got the wrong out of the two. The other thing we could do is to put an extra condition only when variable face to cup distance is smaller than, say, 200 millimeters. So basically, we only want to accept the end drink event when there is still not that much distance between the face and the cup. That was actually my reason for calculating that event in the first, variable in the first place. So that is a small improvement to the variable scheme, to the event scheme in this case. And if I go back and save this, then I can pop back into Nexus, run the ProCalc thing again, and we have 4 events instead of 5. It really is quite cool the way you can swap between Nexus and ProCalc and just do the calculations more or less on the fly. Could we use ProCalc to modify existing models to calculate more variable parameters? This is absolutely possible. So what you might want to do is to, if you, for example, run plug-in gate or any other biomechanical model that you know works, and you load up a trial that already has, for example, the knee joint angles calculated in a way that you're comfortable with, then you can use ProCalc to extract, for example, the maximum knee flexion during swing. So basically, you go into ProCalc and you focus almost exclusively on the parameter scheme. And in here, you would then add like max or left knee flex x max, and this would be a value, and you would pick out a maximum, for example, between 2 events. So in this case, you would pick out the left knee angle from plug-in gate here, and you would pick out the foot off events and the foot contact and the following foot contact event, and then you would get exactly those kind of parameters calculated for you by ProCalc from the results of plug-in gate. Yes. I've tried to use a number without a value in the input parameters, but it doesn't show up as a number to use in the variables tab. Why is this? Very good question. It's obviously possible that it might be a small bug which I haven't noticed before. We can try it. So this is the input parameters webinar. Let's just define a number. So a typical number might just be pi, in case you want to calculate something with pi. It's usually 3.14. give or take, and it's unitless, so it doesn't have a quantity, it doesn't have a unit. So that's pi defined here. And if I want to do some calculations with that, we could, for example, add just we could try and calculate 2 pi by adding a number to a number, and it doesn't appear. You're absolutely correct. Yeah, so that should have appeared under here. Okay, let me try one more thing. Okay, yeah, I think that might be one for the list of issues. I hope it works if I do have a quantity and a unit. Save variables. So this should appear as a length. Yeah, there it is. So it does seem to work if it has a unit. Yeah, sorry about that. Also, why is a negate option available for Euler angles but not continuous Euler angles? Oh, interesting. That could also be one of the. It is available for the continuous Euler angles, as far as I can tell. It doesn't make a difference. Okay. So it's available, but it doesn't work. Okay. Yes. This is also clearly one of the small issues that need to go on the list. So that's good. Keep them coming. It's not perfect, but it's pretty useful tool, I hope. All right. Do feel free to add more questions for those who have them. Can I open a body language model inside ProCalc? This would be fantastic, wouldn't it? But a body language model is defined in a very, very different way. And although you can translate in some ways, you can look at the body language model and look at the script and work out the exact same results in ProCalc. It's not possible to actually automatically do this translation and open it inside ProCalc. What is the use of XMP over MP? The reason ProCalc uses XMP is that the MP file is a text file which does not actually allow you to smoothly store certain types of information very well. The reason ProCalc uses XMP is actually that it needs a more flexible way of storing the calculated values, such as it needs to be able to store the units, multiple components, etc., etc. So the XMP is, as the name implies, an extension to the MP file. The MP file is in either case a little bit like a very historical legacy file format that is, yeah, it's still obviously used, but it's I agree this is not an optimum solution, but it is the way it is, and it couldn't unfortunately be used for the purpose of ProCalc, the MP file, I mean. Okay. I've noticed the body language code and ProCalc calculate coordinate system definitions differently. ProCalc seems to follow the right-hand rule while bodybuilder does not. That is news to me. For sure, ProCalc follows the right-hand rule, as it should. I was not aware that bodybuilder does not. Although in bodybuilder, when you specify the segment, I guess maybe you can also use a left-hand token, such as well, you have X, Y, Z, which would be right hand or something. Yeah, and I'm not really aware of using left-hand coordinate systems in bodybuilder. I'm sure you can also use right-hand coordinate systems in bodybuilder. For sure, email support@prophysics.ch with some more details, and we'll pick it up and have a look. That's absolutely fine. So, any more questions? Anyone? No? Well, I think this is a good time to wrap. It's about an hour and 20 minutes. I thank you all very much for attending, and of course you'll get an email with with a link to look at the recording. Hopefully it'll work this time. And in case you have further questions, then support@prophysics.ch, or for the Scandinavians, they can also email support@prophysics-sol.se. Feel free to email support in case you have further comments or questions. And this is if in case webinars like these are interesting for the future, you can also let us know if you have any ideas for topics that you would like for future webinars to cover. Always welcome to hear suggestions, and we will consider them for future webinars. Now in these pandemic times, it's been a good tool for us to keep, well, educating or having contact with the community. Another little question came. Can we use ProCalc with Shogun and Tracker? Not really. Tracker certainly not Tracker. In Shogun, you could record a trial in Shogun, save it out as a C3D file, and then load the C3D file into ProCalc for calculations. But it wouldn't make any sense the other way. So you could certainly take a trial that you record in Shogun and do some calculations on it in ProCalc in order to get some parameters out, for example, but that's about it. Yeah. All right. Okay. Thanks very much, everyone, and have a nice day, weekend, Pfingsten, Pinse, all that, and see you soon. Bye for now.